am videoing.
Okay. Hey guys, okay, we're gonna work some practice problems so that you can have access to these to make sure that you're clued in for the second half of the module. So this is, I'm jumping with, starting with practice problem number 4, which is where we left off after class last week. So this is number 4, okay? And the question reads, using the enthalpy from problem number 2, calculate the kilojoules of energy that are released when 500 grams of benzene is burned in excess oxygen. Okay, so first of all, we know from problem number 2 that the amount of energy that was released for this chemical reaction is a negative 6,278 kilojoules, okay? Before we jump into the math of it, let's look for a minute at the type of equation we have, which we also talked about in class last week. So we have benzene, which is a compound with carbon, and we're burning it in the presence of oxygen, and we're gonna produce from that carbon dioxide and water. So that means we have what kind of reaction? We have a complete combustion. And we know that all complete combustion reactions are exothermic, meaning they release energy into the surroundings. Now what we calculated from problem number 2 was the amount of energy that is released is 6,278 kilojoules. Now, if you remember from last week, we talked about the fact that if we have an exothermic reaction, we list the energy on the product side of the equation. And if we have an endothermic reaction, we're going to list the energy on the reactant side. This is exothermic, so the energy goes on the product side, but we list it as a positive, and there's a reason for that. When we calculate our change in enthalpy, we get a negative number if it's exothermic, and that tells us that it's an exothermic reaction. However, it is a positive amount. It's not, we don't have negative energy that's released. So that's why we're actually listing the amount of energy as a positive number. It's a positive amount of energy that is released into the surroundings in an exothermic reaction. So let's jump in and get the math done. So they tell us we've got 500 grams of benzene, which is this right here. But of course, in chemistry, we know that we can't relate amounts with grams. We have to turn them into something we can use. And we also know that that's always going to be moles. So we're going to go ahead and convert our benzene into moles. So if I have 500.0 grams of C6H6, which is benzene, okay, I know that for every 1 mole of benzene, I'm going to have 78.1 grams. So when I do this math, I find out that we actually have 6.40 moles of benzene. Okay, so now I got to look at the relationship stoichiometrically between benzene and my energy in this chemical reaction. And I know that for every 2 moles of benzene, I'm going to end up with a production of 6,278 kilojoules of energy. So now I can use this just like I would any other stoichiometric ratio or equivalent and calculate the energy. So if I have 6.40 moles of benzene, I know that I'm going to, for every 2 moles of benzene, putting that on the bottom because I'm trying to cancel them out, I'm going to produce 6,278 kilojoules of energy. So when I do this math, I end up with 20,100 kilojoules of energy. Again, it's a positive amount. This is the amount of energy that will be produced if I start with 500 grams of benzene. Okay, I'm going to erase this and jump into problem number 5 real quick, and then we'll take a break. All right, so that's problem number 4. All right, problem number 5 says, given the following reaction, which is 2NO2 as a gas plus 7 moles of hydrogen as a gas will release 2 moles of ammonia as a gas and 4 moles of water as a gas. Now, here's what the problem asked. It says, if we're given this chemical equation, how much energy will be released if we have 35 grams of ammonia are formed? So what they're asking us is, well, if I produce, oops, that's a terrible bracket. Okay, if I produce 35 grams of ammonia, how much energy is associated with that? But they don't tell us what the energy is. So the first thing we've got to do in this problem is we got to calculate our enthalpy, or our change in energy. So we're going to do that using Hess's law. Now, if we remember back to Hess's law tells us that the sum of the changes in enthalpy of formation of my products minus, I'm going to take that and subtract from that the sum of the changes in enthalpy of formation of my reactants. All right, so I've got Hess's law. This is what I'm going to use. I'm going to start with my products and subtract from that the changes in enthalpy of formation of my reactants. And of course, I've got to use the table provided in the book. I don't know that off the top of my head. So when I do that, I get a delta H that equals 2 moles times of the ammonia times negative 45.9 kilojoules per mole. And I'm going to add to that my 4 moles of my water times negative the energy associated with formation of that, which is negative 242 kilojoules per mole,